So here we study radial engine and we investigate the state of balance of a radial engine. So in a radial engine, all the cylinders, the lines of strokes are arranged as radial lines like this. So suppose you have a you for a 3-cylinder radial engine, these are the maybe the three. So this is how the cylinders are arranged, and there is a common crank. Maybe this is the common crank. So this is how it is arranged. So all the lines of strokes, they are actually now radial lines, and the angular interval between them, this is the angular interval between them. For a 3-cylinder radial engine, it is actually 120 degree, as you see. So angular interval between them is twice pi by n. So here for a radial engine, only 3 cylinders are shown, but this is actually a radial engine like this, consisting of n number of cylinders. And since there are n number of cylinders, this angular interval is twice pi by n, and this is the common crank. So in radial engine, you remember the crank is common. So this is twice pi by n, this is twice pi by n, another radial line for the 4th cylinder, another twice pi by n. And this is the crank which is making theta with the vertical. So the vertical force is m omega square r cos theta. M omega square r cos theta is the force along the line of stroke for the first cylinder. For the first cylinder along this line of stroke, the force is m omega square r cos theta, and the component along the vertical direction is cos theta cos 0. So for the second cylinder, the force m omega square r cos theta is along this line, and you have to take a component along the vertical direction. So it is actually, so from this line, the angle is theta minus twice pi by n. So the force is m omega square r cos theta minus twice pi by n, because for this theta becomes theta minus twice pi by n, because from the line of stroke the angle of the crank is theta, so which is theta minus twice pi by n here, and that is along this line. So now if you take component in the vertical direction, you have to multiply it with cos twice pi by n. Then for the next one, it is cos theta minus another twice pi by n, so 4 pi by n into, and the component along this is cos 4 pi by n. In this you have to continue up to n terms. So actually this is twice pi by n, this is twice pi by n, and this is 2 into twice pi by n, and if you go to the nth term, it would be twice, this is 2 into twice pi by n, so this is n minus 1 into twice pi by n for the last term. For the last term it is n minus 1 twice pi by n. Anyway, so cos theta cos 0 can be written as half cos theta plus cos theta. Cos theta minus twice pi by n cos twice pi by n can be written as, this is cos a cos b, so this is cos a plus b plus cos a minus b, so this, and here cos theta minus 4 by n cos 4 by n cos a minus b plus cos a plus b, and this is the last term, cos theta minus, in place of 4 pi by n we write 2 into n minus 1 pi by n. So and here again cos component along the vertical direction, it's 2 into n minus 1 pi by n. So now if you use the formula cos a cos b equal to half of cos a plus b plus cos a minus b. So cos a minus b plus cos a plus b. So this is what you get. And now see, so all these terms you have to, if you add up, then this is the first term n cos theta, and if you add these terms cosine series with the difference in the angle, common difference in the angle is 4 pi by n. So if you add them up, so you get this. So this is n cos theta plus this. So this is 0, this is 0 because this is 0, but the denominator has to be non-zero. So if n is greater than 2, then the denominator is non-zero. If n equal to 2, if n equal to 1, the denominator is 0. For n greater than 2, the denominator is non-zero. So this term cancels out. For n greater than 2, that means a 2-cylinder radial engine, that is 180 degree apart. So for this you get n m omega square r, n by 2, m is half is there, n by 2 m omega square r cos theta, this is the vertical force, and n by 2 m omega square r sin theta is the horizontal force. So this is the vertical force, this is the horizontal force, and this is the position of the crank. So if you add a balancing mass in the opposite side of the crank, then you can balance the primary unbalanced force. So primary unbalanced force can be balanced by a mass n by 2m opposite to the crank rotating with the crank, but it depends upon also the distance. So this is the balancing mass mb into the distance at which it is placed b, it has to be equal to n by 2 m omega square r. And when this b is equal to r, then only this mb is equal to n by 2 into here 1 omega square come n by mb equal to n by 2 m. So nb equal to n by 2 m when this b is equal to r, otherwise it will not be equal to n by 2 m. So now if you go for the higher harmonics, so we and take the horizontal component. So suppose if b 2k, we are writing 2k in place of m, we are writing 2k because we now assume that k is the integer which varies like 1 2 varies as 1 2 3 like this. For if you had you written m in this place, then m would have varied like 2 4 6 like this. So this is m omega square r, a constant, then cos twice k theta because it is a twice kth harmonic. So the first is along the first line of stroke and the component is cos 0. The second force is twice k multiplied by theta minus twice pi by n. For the primary one it is only cos theta minus twice pi by n. For the twice kth, for the secondary it is 2 into theta minus twice pi by n, and for the twice kth it is twice k into theta minus twice pi by n, and it is along the line of stroke of the second cylinder. So the component is cos twice pi by n in the vertical direction. So in this way you can continue and go up to n terms. So this term cos 2k theta is half this, and the second term, this term cos 2k theta minus twice pi by n cos twice pi by n, again cos a cos b equal to cos a minus b plus cos a plus b, So if you write it like this, it is this. So the next term is this. So it is first one twice k theta, then minus twice k minus 1 2 pi by n. This is 2 into twice k minus 1 2 pi by n. This is 3 into 2k minus 1 twice pi by n. Like this it goes on. And for the last term it is actually n minus 1. So for the second it is 2k minus 1. For the third it is 2 into 2k minus 1. For the fourth it is 3. So for the nth it is n minus 1th 2k minus 1 into twice pi by n. And similarly for the second term. So now if you add this cosine series, then you get this, and if you add this cosine series you get this. So this is 0, this is 0, and similarly for the horizontal force also you get a similar expression. So please check this expression. So see this 2k minus, so for k equal to 1 2 3 4, this is 0, this is also 0, similarly this is 0, this also is 0, but you have to check the denominator. The denominator has to be non-zero, and for that 2k minus 1 by n and 2k plus 1 by n, 2k plus 1 by n has to be non-integral, non-integers. So 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 here 2k plus minus 1 pi, it is 0, always satisfied, but you have to have both of these non-zeros. That means twice k plus minus 1 has to be non-integer. So if n is even, then twice k plus minus 1 is always odd, then it is non-integer, and this condition is always satisfied. So a radial engine with even number of cylinders, the higher harmonics are balanced. For radial engine with even number of cylinders, the higher harmonics are balanced. But for odd number of cylinders, you have to individually check whether twice k plus 1 by n and twice k minus 1 by n are integers or not. If they are integers, then it is not balanced, and if they are non-integers, then it is balanced. So fix n, so take your number of cylinders and you check k equal to 1 2 3, the harmonic number, the second harmonic, fourth harmonic, sixth harmonic, and you check 2k plus 1 by n, 2k minus 1 by n. So if they are integers, then that harmonic for this n number of cylinders is not balanced, and the lower order of the lowest balanced harmonic, so what is the smallest value of k which you can get for unbalanced, that is your this for smallest value of k, twice k by n, it should be equal to 1. This is for the smallest value of k. So k is, or twice k rather, is n minus 1. So this is the smallest harmonic which is, this is the smallest harmonic which is not balanced. This is the smallest harmonic which is not balanced. So now you can look at this table. So suppose this is the value of twice k, this is the value of actually the harmonic, twice 4th, 6th, 8th, 10th. So and this is the value of number of cylinders. Suppose you take 3 as your number of cylinder, and if the harmonics are not balanced, then these are marked crossed. They are cross marked. So for capital N equal to 3, that is number of cylinders equal to 3, 2k plus 1 is 2 into the 6 plus 1 by 2. For okay, for if you go for, sorry, for number of cylinders equal to 3 and 2k equal to 2, that is 2 plus 1 by 3, that is 3 by 3 is an integer. 2 minus 1 by 3, that is 2k minus 1 by n is not an integer, because 2 minus 1 is 1, 1 by 3 is not an integer, but 2 plus 1 by 3 is an integer. So this harmonic, second harmonic is not balanced. The fourth harmonic, for the fourth harmonic, 2k is 4, so 4 plus 1 by 2 is 5 by 2, non-integer, okay. But 4 minus 1 by 2 is 4 minus 1 by 3, 4 minus 1 by 3, 2k minus 1 by 3, 2k minus 1 by n, that is 4 minus 1 by 3 is an integer. So no, not balanced. But for 6, 2k equal to 6, 2k minus 1 by n is 2k minus 1 by n is 6 minus 1 by n, so 5 by 3. So yes, it is non-integer. And 6 plus 1 by 3, that is also a non-integer, because that is 7 by 3. So this is balanced. So in this way you have to individually check for odd number of cylinders. But for even number of cylinders, there is always all the harmonics are balanced.